In a data center environment, proper grounding is critical for safety and equipment reliability. When dealing with transformer secondaries, it's essential to understand the correct grounding practices to prevent ground loops and ensure a safe, functional system. The primary recommendation is to connect the transformer secondaries to the main grounding busbar, or MGB. This approach ensures that the transformer secondaries are properly grounded while also minimizing the potential for ground loops. Ground loops can occur when there are multiple paths to ground, creating a circulating current that can interfere with sensitive electronic equipment and pose a safety hazard. It is strongly advised against connecting the transformer secondaries directly to building steel. Connecting to building steel can inadvertently create a ground loop if the building steel is also connected to the utility power neutral or the multi-grounded neutral. This situation effectively creates two separate grounding paths, potentially leading to a difference in potential between the two grounding points and thus a ground loop. Utilizing ground bars within the data center is a good practice, as long as these ground bars are also connected back to the MGB. These ground bars provide convenient and reliable grounding points for equipment racks and other devices. Connecting the racks to these ground bars, which in turn are connected to the MGB, ensures that all equipment is properly grounded and connected to a single, defined grounding point. When implementing a grounding system, there are several additional considerations to keep in mind. Firstly, ensure that the MGB is adequately sized to handle the potential fault current. The size of the MGB is determined by the anticipated fault current levels within the data center. A properly sized MGB will provide a low impedance path for fault currents, allowing protective devices to quickly clear faults and minimize equipment damage. Secondly, the MGB must be properly bonded to the building steel and the utility power neutral. This bonding ensures that all grounding points are at the same potential, reducing the risk of ground loops and ensuring a stable ground reference for all equipment. Thirdly, consider implementing a grounding ring. A grounding ring is a copper conductor that is installed around the perimeter of the data center and connected to the MGB. This ring provides a low impedance grounding path and helps to equalize ground potential throughout the facility. It enhances the overall grounding performance of the data center, particularly in large facilities where ground potential differences may be more pronounced. Finally, it is crucial to perform a ground loop impedance test once the grounding system is installed. This test verifies that the grounding system is properly installed, that all connections are secure, and that there are no potential ground loops present. The test involves injecting a test current into the grounding system and measuring the impedance of the ground loop. A high impedance reading indicates a potential problem with the grounding system. Understanding the explanation behind these recommendations is vital. Connecting the transformer secondaries to the MGB establishes a clear and controlled grounding path. The MGB connected to the utility power neutral at the multi-grounded neutral provides a low impedance path to ground. The single-point grounding approach minimizes the risk of creating multiple ground paths and potential differences that could lead to ground loops. In contrast, connecting the transformer secondaries to building steel could create a problematic scenario. If the building steel is also connected to the utility power neutral, this creates two grounding paths. The potential difference between these paths can drive current through the grounding system, leading to equipment damage or even injury to personnel. Grounding bars connected to the MGB offer a convenient and reliable way to ground equipment racks. This configuration ensures that all equipment is properly grounded and connected to the main grounding system, further reducing the risk of ground loops. To reiterate, the key principles are single-point grounding, low impedance paths, and thorough testing. By following these principles, data centers can establish a robust grounding system that protects equipment and personnel. Ensuring the correct size and bonding of the MGB is paramount for effective grounding. Fault currents can be substantial, and the MGB must be capable of handling these currents without creating excessive voltage drops. Proper bonding to building steel and the utility neutral ensures that all grounding points are at the same potential, minimizing the risk of ground loops. The use of a grounding ring is another proactive measure to enhance grounding performance. By encircling the data center, the grounding ring provides a low impedance path to ground and helps to equalize ground potential throughout the facility. This is particularly beneficial in larger data centers where ground potential differences may be more significant. After installing the grounding system, it is essential to perform a ground loop impedance test. This test verifies the integrity of the grounding system and ensures that there are no unintended ground loops. The test results should be carefully analyzed and any issues promptly addressed to maintain a safe and reliable grounding system. In summary, data center grounding requires a meticulous approach. Connecting transformer secondaries to the NGB, avoiding direct connections to building steel, utilizing properly connected ground bars, ensuring the NGB is adequately sized and bonded, considering a grounding ring, and performing thorough testing are all crucial steps in establishing a robust and reliable grounding system. Understanding the principles behind these practices is essential for ensuring the safety and reliability of data center operations. The avoidance of ground loops is a primary concern in data center grounding design. Ground loops can arise from multiple ground paths, leading to circulating currents that can interfere with sensitive electronic equipment. By connecting transformer secondaries to a single point, the MGB, the potential for ground loops is minimized. The building steel, while often grounded, should not be used as a primary grounding path for sensitive equipment. Direct connections to building steel can create alternative ground paths, increasing the risk of ground loops. Ground bars strategically placed throughout the data center provide convenient grounding points for equipment racks. However, these ground bars must be properly connected to the MGB to ensure that all equipment is grounded to a single, defined point. The MGB serves as the central grounding point for the entire data center. Its size and bonding are critical to its performance. The MGB must be capable of handling the maximum anticipated fault current, and it must be properly bonded to building steel and the utility neutral to ensure stable ground reference. A grounding ring encircling the data center and connected to the MGB could further enhance grounding performance. The grounding ring provides a low impedance path to ground and helps to equalize ground potential throughout the facility. After the grounding system is installed, a ground loop impedance test is essential to verify its integrity. This test identifies any unintended ground loops and ensures that the grounding system is functioning as designed. Grounding is not a static aspect of data center infrastructure. It requires ongoing monitoring and maintenance to ensure its continued effectiveness. Periodic inspections should be conducted to verify the integrity of grounding connections and to identify any potential problems. Regular ground loop impedance tests should also be performed to ensure that the grounding system remains free of ground loops. By following these best practices, data centers can establish a robust and reliable grounding system that protects equipment and personnel. The key principles are single-point grounding, low impedance paths, and thorough testing. Understanding these principles is essential for ensuring the safety and reliability of data center operations. Remember that local electrical codes and regulations may also dictate specific grounding requirements. It is important to consult with qualified electrical engineers and to adhere to all applicable codes and regulations when designing and implementing a data center grounding system. Ultimately, a well-designed and properly maintained grounding system is essential for the safe and reliable operation of any data center.